So the second part of topic 2, part 1, has to do with calculating the atomic mass of an element. So last class we talked about atomic number, I'm going to use shorthand here, and mass number. And so I want to make it very clear, these three terms are all different things, okay? Atomic number, if you remember, is the number of protons that are in the nucleus. That's an O. The mass number is the protons plus the neutrons added together. Okay, so both of these values will always be whole numbers because it's a count of particles. It's the count of the number of protons, or in this case, the count of the number of protons and neutrons together. Okay. Atomic mass, however, is different. Atomic mass is actually an average calculation. And in fact, it's called a weighted average. So there you're going to see that term used here. And a weighted average just means that not everything counts for the same amount. So it's kind of like how your grades are done, at least in our class. Not every teacher does this, but for example, your major grades, because we typically have less of those, we have less tests and less projects, those are weighted 30%, whereas your minor grades, the things that we do daily and the things that we do more often, those are weighted 70%. And so that way they tend to weight a little bit differently. So it's kind of that same concept here. Not everything is 50-50. Okay, it's not everything's equal. So when you do this kind of average, I'm not just going to add my numbers up and divide by, the number that I had to add up. Okay, it's different. And so what we're going to do is we're going to talk about how to calculate that today. And we're also going to talk about how they figure out some of these numbers, because, it's kind of like, well, where did these numbers come from? Did somebody just make them up? No, somebody did some experimentation and they measured some data, and that's how we have this information. So, atoms, as we know, are very, very, very small. Okay, as we can see here, they're somewhere between 10 to the negative 24th and 10 to the negative 22nd kilograms, depending on which element we're talking about. And so because they're so small, we use a relative scale. Relative meaning that we're comparing it to something else. Okay, it's relative to that thing we're comparing it to. And so the standard that we use for relative atomic mass is the isotope carbon-12. And the reason for that is because carbon-12 has exactly 6 protons and 6 neutrons, so its mass is exactly 12. And so they assign carbon-12 the mass of exactly 12, and then they compare everything else in relation to that carbon-12 atom. And so in this box, this is very, very important. This is a definition that could pop up on a test question on your IB exams, because they like to make sure that you guys know proper definitions. And so the relative atomic mass is the weighted average mass of an atom compared to, and this is the important part, is this last part, compared to the atom of the isotope carbon-12. Okay, because in first year chemistry, we really talk about that first line. We know that it's a weighted average mass, but we don't really go into detail about comparing it to the atom of the isotope carbon-12. So make sure that you include all of that in a definition if you're asked about that question. The other thing I wanted to point out right here is that because it's a relative atomic mass, it does not have units because it's a relative scale. So because I'm comparing it to something else, there's no units of measurement. And so relative atomic mass, typically it's just a number because of that. So where do we get the numbers that we use for these calculations? Well, I'm glad you asked. There is a machine that is called a mass spectrometer, okay? Mass spectrometer. We used to have to know how this whole machine worked, but they removed that from our IB curriculum, so we don't have to know that. But I just wanted to kind of briefly go over the parts of it just to kind of explain how this works. And so this machine, and what they do is they inject a sample of the element kind of in this one end. And when they inject it in, it's heated up until it becomes vaporized. It becomes a gas. So if it wasn't already a gas, like if it was a liquid, which a lot of times it's a liquid, it will be vaporized and turned into a gas. It'll go from liquid to gas. And then as soon as it's turned into a gas, then there is an electron gun in here that fires at it, and that turns the sample from atoms to ions, and so that's called ionization. And the reason that we want them to be ionized is because we want them to have that either that positive or negative charge, because that's going to impact the next couple of steps, okay? After they're ionized, then they go through an electric field, and when they go through the electric field, that actually causes them to accelerate, so they move faster, speeds them up. And then they reach this bend, and this bend, okay, you see this box here, there's kind of a magnetic field around that area. And so what happens is magnetic field has a positive and a negative side, right? And we've now made these into ions, so they have positive and negative charges. So what happens is the magnetic field will deflect the ions because it will usually cause them to turn at different angles. Because of those charges, they're, repelling and things like that. But what happens is the larger the atom, the less it deflects. And that kind of makes sense if you think about it. Like, if you think of something larger, usually that moves slower, right? And something that's smaller is usually like a lot faster, okay? So that's what happens, is that they get deflected, but they get deflected at different angles. So, maybe one of them gets deflected here, but then maybe another one is deflected kind of like this. And then if there's a third one, maybe the third one's like all the way out here. Okay. And so then what happens is at the very end, there is a detector. And so what happens is after they're deflected through that field, the detector, it reads out the data and it creates this mass spectrum. And so a spectrum is where we just see things across an area. And so what the mass spectrum readout looks like, this is an example right here. Okay. And what happens is you have an X and a Y axis, just like graphs and things in math and charts. And so what happens is on your Y axis, you have relative abundance. Okay. Relative abundance is your percentage. Okay. And then on the X axis, that's where you have what they call the mass to charge ratio. The mass to charge ratio, that's just telling you the mass. Okay. So this is going to be my mass. And so how I would read this is the mass spectrum for lead, which is the element Pb, is shown below. So if you're given a chart like this, here is how you would need to use this data. Okay, I would look at each of these lines, each of these vertical lines, and I would say, okay, this one, it has a mass of 204, and the relative abundance is 2. Now, here's the catch, okay? The relative abundance, I told you that's a percentage. So that 2 right here, that's 2%. So before I can use it in my calculation, I have to get rid of that percent, which means I have to convert it to decimal form, which means I have to divide by 100, because that's what a percentage is. It's out of 100. So if I have to do that, then I'm going to say, okay, here's my decimal, because this is a whole number, it's 2. And if I divide by 100, that means I move the decimal 2 places back to the left. This is like the most important step. If you forget to move the decimal, then you will get your answer wrong because you forgot that step before doing your calculation. Once you have changed that percentage to the decimal form, so now instead of 2%, now I have 0.02, now that gets multiplied by the mass for that isotope. So this graph, this sample, it actually has 4 isotopes. And I can tell because it's got 4 different vertical lines, okay? There's the second one, here's the third one, and then here's the fourth one. So that means for my calculation, I'm going to have 4 different things that I'm going to add together. So see how I did the 204 times the 0.02? I'm going to do that for the other ones too. So the second one would be 206. Now its percent was 24%. So if I want to change that one, then that one would only be 0.24 in the decimal form. So that's my second one. My third one is 207. And then I'm going to multiply by its percentage. Its percentage, if I look at the top, it's 22%. And so I would move the decimal back twice because that's dividing by 100. So that makes it 0.22. And then I'm kind of out of room, so I'm going to write over here to the side. But my last one is 208. Actually, let me move that over a little bit. 208 times, now this one, the percent is 52%. And so that one, if I move the decimal back twice, that makes it 0.52. So for every isotope in your sample, so on this graph we had 4. It might not always be 4. It might be 2. It might be 3. It might be 8. Okay, it just depends on the element. So for each isotope, we do this process. We multiply the mass by the percent in decimal form. And so when I multiply these, so for this first one, when I multiply these, I get 4.08. For the second one, when I multiply this, I get 49.44. For the third one, when I multiply this one, I get 45.54. And then for my last one, I get 108.16. Okay, that's that last one. So once I've multiplied each isotope's mass by that percent abundance in decimal form, then my last step is to add them together. So I'm going to do a different color here. So I kind of put a plus sign here. I'm going to add them together. And when I add these together, I get 207.22. And remember I told you there's no unit, so that's it. There's no, it's not grams, it's not anything else, okay? It's just 207.22. Now, a couple other things you could be asked about average atomic mass questions like this, or relative atomic mass. If you are shown this graph, okay, like this, they might ask you a question like, which of the isotopes is the most abundant? If they ask for the most abundant, you are looking for which one has the highest peak, okay, because that's got the highest percentage, and it's this one right here. It's this one because it's got 52%. So I would say the lead, or the PB208, or the lead 208. That's the name, or that's the name of that isotope. It's lead 208. That one is the most abundant because it's got the highest abundance, the highest number, and I can tell because its peak is the highest. If I was asked the opposite, if I was asked what's the least abundant, the least abundant is going to be this one. So lead 204 is going to be my least abundant because it has the lowest peak. It has that lowest percentage number. It's only 2%. So those are a couple things they could ask you. And another thing I want to point out is look at our most and least abundant. If we look, the most abundant was this 208, and look at the average. It's really close to that. If you look at all the numbers, we got 204, 206, 207, but because 208 had 52%, it caused the average to be above that 207. And so a lot of times your most abundant isotope will cause your average to change more because that has a bigger effect on it, okay? Just like how, on your grades, the ones that count for the higher percentage will have a more effect. So you guys down here have some practice. Now, these are a little different. They are not given in that graph form. They simply have given you the percentage. Okay, so for example, on this one, here are the percentages. And then how do I know where the mass is? Well, they gave us the symbol of the isotope. And so remember the number in this top left corner, that is the mass number. So on this one, you only have 2 isotopes. Okay, so you're only going to do what we did right here twice. You're going to have 2 masses, and you'll multiply each of them by their percentages in decimal form. Don't forget to change them. And then you'll add those 2 answers up. Now, on letter B, there's a lot more isotopes. There's 7 isotopes on this one. Okay, and the percent sign just got left off on that one. That's still a percentage. Okay. The last couple of things on here right above where this practice starts, just to kind of go over really quick, is that, like it says here, and this is what I summarized earlier, that our ions that have lower mass to charge ratio are deflected more. So the smaller ions, the smaller atoms, they deflect more. The ions that have higher mass, they're going to deflect less. And so that's what we kind of see on the readout of this graph, or from this machine, is that the ones, so for example, on the lines that I drew right here, the purple deflected the least, and so that would probably be the heaviest. The red deflected the most. That one would be probably the lightest on this one. Okay, so Don't forget you have, let's see, what do you have? 1, 2, 3 problems to do. Okay, so you don't have a lot, but you have a few to do, just with that process that I just did right here. Okay, and then you will make sure that you get that submitted and turned in on Canvas. And I will go see you guys in class to go over some questions.